welcome in. Let's do a little bit of practice now that you've gone through quite a lot of derivatives. So starting off with all the different rules that you had, primarily for kind of power functions, which led into polynomials, and then rational functions, again, just with really polynomial in the numerator and denominator. You glanced into stuff related to sinusoidal functions, so from sine and cosines and tangents and so on. And then you dived into exponential derivatives. So now what I want to do is I want to kind of combine all of those, and this is part of the exponential chapter that you would be doing in kind of first calculus. The examples that I present probably are going to be a little bit more challenging than most, but I really want you as a student to be able to go through and take any function, doesn't really matter how complicated, and be comfortable with applying the rules for derivatives. So if it's constants, okay, if it's additive or subtractive, okay, so that you have in there, if it's a product rules that you're using, quotient rules that you're using, so for composite functions, so the chain rule, okay, so that you're all comfortable with those and being able to apply them and being able to kind of extract each functions and then the parent functions themselves as well. So it's not a super complicated video, I hope, and I do intention this to be more of a practice than anything, as you have gone in and introduced yourself to the new exponential derivative. So I'll write it here on the side just so that we don't forget. So for example, the derivative of e to the x, so if you take the derivative right there, we know that this is just e to the x, and I've shown you how that actually comes about. It's an amazing result with respect to the derivatives. I can put up a link up above there. And then the general case that you have, so this is for any base, doesn't have to be e. So for any base b, which is between 0 and 1 or greater than 1, if you take the derivative, again, it's not as nice as this one, almost, but it does have a constant in front, so that will be ln of the base multiplied by the function itself, so b to the x. So we have to remember these, of course, to be able to do derivatives throughout. And I'll put this on the side here, okay, for us. And that second one, so the ln b times the base to the x, so if that derivative, if you want to see how you can come up with that derivative and prove it, okay, I'll put up a link up above there for you. So let's begin these. All I want to do is just take derivatives, and again, a derivative is really just a function. It tells us what the slope is at every single point of the function where the slope is defined, so where the derivative is defined. So here's the first one that we're going to do. So I'm going to copy this. Let's bring it down right here, and let's take now the derivative. So if we want to take the derivative of this, okay, now this is with respect to x, then we would have is, we really are seeing two functions here. So there's an x, and then it is multiplying this exponential, and the exponential itself actually has 3x in the exponent. So right away we would use the product rule within here. So what I would do is I would take the product rule to start off, and the derivative of the first one that I would have, so this is just 1, and then 1 times this would have just given me 3x. And again, because it's product rule, so this is going to be plus, and now I have to take, so the x actually stays behind, and now I have to take the derivative of 2 to the 3x. And that, okay, I'm going to use this right here. And so for this, so what I'm going to have is, I'll put it in brackets, I'm going to have ln of 2, that is the base, multiplied by my actual function back. And now the problem is, that I also have here, so 3x, so I have to use the chain rule, and this is going to be times 3. So that is the actual derivative of the whole thing. So this would have been 3x, I can extract that whole thing out. I'm going to get 1 plus, so meaning I can factor it out there. And then I'm going to have 3, I'll put that in the front, so 3 times ln 2 of just simply multiplied by x, because I took out that 2 to the 3x right there. This is what I would have. Now, would there be any restrictions in here with respect to x? No, not really. You know, everything is in the numerator, so our domain is very nicely defined in here. We have an exponential, okay, so this derivative is nothing else but an exponential right here, multiplied by this, which is really just kind of a 3 ln 2, okay, is just a constant, so this is really just a line. So that's a nice derivative that we have. So that's the first example, and it utilized the product and the chain rule that we had right here. So it used this product rule, and then it used the chain rule right there. So those are the two that it utilized. Let's take a look at another example. So here is another example. Let me copy this, bring it down, and let's try to take the derivative of this. So what would this be? I'll change colors here. So we'll take the derivative, and this is going to be with respect to t. So notice that it is t now that I have. This one's going to be actually a little bit easier to do. So I have a constant right in front, so nothing happens. So that constant just remains there. It's going to get now multiplied, and it's going to get multiplied by the derivative of e to the negative 2 over t. That's going to be just the actual function itself. So that's going to be that. But now I need to use the chain rule for this right here, right? Because I have negative 2 over t. So I need to find out what the derivative is of that. And so here I'm going to write it on the side here for myself. So this is negative 2. Okay, and if I bring this up to the numerator there, so it's going to be that. It's the same thing. So notice this is going to be the negative and negative will cancel. This will be 2. And this is going to be t to the minus 2. And that is your whole derivative. And now for this one, you know, if you wanted to write it out in full, and you want to put this, and you don't want to have this negative exponent right there. So this is going to be my, whoops, this is the t is in the, sorry, the 2 will multiply the 4. So this is actually going to be 4 times 2, right? 4 times 2, which is going to be 8. That is that. And then the t squared goes at the bottom. So notice, you know, t cannot be equal to 0, because we would run into a problem in the denominators. And it will be, we would have the same problem over here, because negative 2 over t, if it can't be 0 again, because we're going to get undefined there. So that is now your second derivative. So again, now I used quite a few things. So within here, so I had a constant. So in terms of my rules, so I've used this really, right? So for a constant, so that constant stays in front, and you take the derivative of the function. Then I utilized, I guess, my chain rule within there, because I had e to the negative 2t, and that is your derivative. So that's the second example. Let's keep going. So these get a little bit more challenging as we go through. So I'm not going to simplify these much anymore. I just want to be able to show you that these are certainly doable. So here is a combination, and we want to find now the derivative. And this one's going to be a little bit annoying because it's a relatively big function right there. This is with respect to x, I guess. So we have an exponential, and it is multiplying sine 2x plus cos 2x. All right, so, you know, so for this one, I mean, if I leave it as it is, you can certainly bring this inside of the brackets, right? So you can multiply this inside of here. We don't really have any restrictions on x here. So we have e to the x, which is very well behaved. Sine 2x, again, you know, it's defined for all x unless we put some restrictions, but there's none here. And then cos 2x is the same. So this is actually defined for all x. So that's pretty good. So now, if you wanted to bring that inside, you know, you're going to be running into a little bit of an issue, okay, in there. Let's not bring it inside. Let's try to use the product rule. So what I'm going to do is I'm going to treat this as one function right here, and I'm going to treat all of this junk So this bracket is going to serve as my second function. So the product rule will be in between those two. So that means I'm going to take the derivative of e to the x, which is just e to the x. And that's going to give me this back. So sine, I'll leave it like this and kind of bring it together. All right, so that is that. And then, so since it's the product rule, so this is going to be plus. And interestingly enough, this is still going to be e to the x. But now I need the derivative of that bracket. Okay, so within that bracket, so if I take the derivative of sine, well, the derivative of sine is cos. So this is going to be cos 2x. And then inside there, I need to apply the chain rule. So that's going to be times 2. So I'm going to have that right there. And then the derivative of cos, okay, so notice there's an addition there, but it's going to be negative sine. So this is going to be turned to negative. This is going to be negative 2. This is sine and 2x. And that is the derivative of that entire thing. So I can put this in here, make it a touch smaller. Hopefully it will fit there, and not so much. So let me shift this over. All right, I'm going to shift that over, and I'm going to put this, okay, right here. So that's going to be right there. All right, and I'll put brackets around, and there you have it. So nothing really special there. Actually, this one is not bad. You know, you can certainly try to simplify it because of the fact that you can take the e to the x out. So factor it out and then see if you can play around, okay, with those, because notice you have sine 2x and then minus 2 sine 2x. So, you know, that could actually cancel off, and you can simplify this a bit. So what I'm referring to there, maybe I'll do it. So I'll take out the e to the x, all right, and then this is going to be sine 2x, that's this one, right, is going to get left behind there, plus cos 2x, that's that. And now the e to the x has come out, so this is going to be now plus 2 cos 2x minus 2 sine 2x, and that's all in brackets. And this is what I'm referring to, that this and this right here, right, can converge together, and then this and this, these are like terms. So I'm going to take these two first, so that's going to be 3 cos 2x, and then so sine 2x minus, so it's going to be minus sine 2x, and this is much smaller, all right, than we had before. So that would be your derivative right there, and again, there's really no restrictions on x here. All right, so that's a good one. So that's number 3 there. So we're moving along. Here is, I guess, going to be a quotient rule that we're going to apply. There's luckily no sines or cosines there, so this one shouldn't be too bad, at least I hope, although it may get a little hairy for us. All right, so this one is with respect to t, so let's take the derivative with respect to t right here, and we have, so we can apply a quotient rule, so we have 1 right there, and then we have another 1 right there. So those are 2 functions, and those functions are actually functions that you see there. There's a product, so this one is actually not going to be as nice, so let's see it. So I'm going to apply, so the quotient rule, so this is, you know, this right here, so we're going to be applying this right there. Can bring it down there just so that we can kind of remember. Paste back, let me paste it over here on this, on the side. So where my f1 is the numerator and f2 is the denominator. All right, so well, the derivative of the numerator is actually not that pretty. So the derivative of this, so notice it's a product, so this is going to get pretty annoying. So it's going to be 2 and then t squared, so that's going to be 4t, right? So that's the derivative of that, multiplied by 3 2t plus, because it's the product rule up on top there. And then it's going to be 2t squared, so we leave that alone, multiplied by the derivative. And the derivative there, so this one is going to be So 3 to the 2t. So that's going to be ln of 3 multiplied by 3 to the 2t and multiplied by, notice there's a 2t there, so I have to multiply by 2. All right, so let me kind of massage this a little bit in here. So that's just the derivative of that numerator there. That's going to be 4t times 3, 2 to the t plus. Okay, so now I'm going to collect all these constants in here. So 2 times 2, so that's going to be 4 ln 3 times, I guess, t squared times 3 2t. And that's just the numerator right there. So I have to take this, and let me make this smaller. There we go. And then this is going to be multiplied by t squared minus 2t squared, right? And then it's minus. Now I need the, this is going to stay, so 2t squared times 3 2t, and now the derivative of the denominator, this one luckily, hopefully is going to be a little bit better, so that's 2t, the derivative of that, minus, well, this one's not going to be actually that nice, so this is ln 2, and this is times 2t squared multiplied by 2t. Oh boy. All right, and then all of this would have been divided by, that's going to be the denominator squared. I'm not even going to try to simplify this. So this was definitely one of the uglier ones. But, you know, as you can see, I'm just using product rules, quotient rules, chain rules, right? The constant, okay, rule, the addition, or in this case, the subtraction. So I have all of these different rules which I can apply for my derivative. And the derivatives certainly look ugly. I don't know if your teachers are going to give you stuff like this, but I like giving this because it forces you, you know, to think about all the rules, you know, kind of put a checklist in your mind and step slowly through the whole thing. You're probably going to make mistakes. I certainly do make mistakes on these. So don't get flustered. Okay, just go slowly through the entire process. So that was another example. There's only one left there. Okay, so this last one, this one doesn't look good, but maybe it's going to be better than the one that we just did. This one uses, you know, there's tan and secant. So, you know, we're going to have to kind of remember our derivatives for those. So if you remember, so 10, well, I'm using y there, so I'll use y. So the derivative of tangent is secant squared, right? And then the derivative of secant y, oh, no, I have to remember this. It's secant y times tangent y. That's the derivative. So those are the derivatives we have to keep in mind there as we're going to be walking through this. There is an exponential there. It's an argument. So let's walk through this whole thing. Let's try to take the derivative of this entire thing. And this is with respect to y. At least that's what I'm going to make it because I see the y is there. The pi is just a constant. So, okay. So I have negative. So this is negative pi. And now I'm going to be, so that can be right in front. And now I can use the product rule. And the product rule is going to be used for these two. So here's my one function, and then here's my other function. So if I use the product rule there, so let me take the derivative of the 10. So as I said, so that's going to be secant squared, so 3e to the y. And it will be multiplied by the derivative of here, of that, which is going to be just, I guess, 3, and this is going to be ey, because that is the derivative that we have there. Okay, so that's that, and that is multiplied by the secant of y. So again, I'm going to use the product rule there. Let me shift this back a little bit. So I took the derivative. So this is the derivative of the first function. And then it's just multiplying secant y. And now it's going to be plus. And this is going to stay the same. So 10 of 3e to the y multiplied by the derivative of the secant. Well, the derivative of secant is actually secant y times 10y. And then I can close my bracket. Now this will, actually the other one will as well. So there are going to be restrictions on your domains, right? Because we do have denominators in here, and you had denominators in there as well. And so for this one, because, 10, so as you recall, it's not defined everywhere. So 10 is sine over cos. So wherever cos was equal to 0, okay, so we would have to be careful there as we're going through. So that would have been as easy to find out. But in terms of the derivative itself, so just testing ourselves on the derivative, this is it. This is how we could go through the whole thing and then find our derivatives. You can simplify this a little bit further. You can certainly take out quite a few things from here to make it easier on yourself. But I typically just leave them, unless, your teacher's mean and says, please simplify as much as possible. Derivatives you just want to kind of keep. And this is, again, these are just made up functions. So they're really just made up in a hard way to test you. You're going to be dealing with real functions, which are much, much simpler. And the goal is, if you can do the derivatives for these, you can certainly do the derivatives for much easier functions. All right, so that is it for this particular video. So quite a few examples in here to test your abilities and then apply all the actual rules for derivatives with now exponentials. Okay, thanks for watching. We'll see you in a future video. Bye, everybody.